Hi, everybody.
Hello.
Okay.
Professor,
Yes.
I just have a quick clarification question about, I noticed you posted homework 8, but one of the problems on there is on our current homework too. Is that intended?
That's obviously not intended. Sorry.
'Cause it looks like it's an application of Fubini's theorem. I don't know if it was supposed to be on homework 8, but it's actually on homework 7.
Oh dear. Um, Let me see 1 second. So on homework 7 is from chapter 2. There's exercises 3, 4, and 9, right?
Yeah, it's exercise 4 is the one that overlaps.
Ay, ay, ay. I think okay. Well, um the there's a perfect solution to this. There are 6 problems on homework 7. Homework exercise 2 is no longer on homework 7 and is on homework 8. So
Oh,
sorry, I'm going to fix this. This is my mistake. This is accidental, and I'm not sure why I put an application of Fubini's theorem on homework 7. Um, so I want to remove problem 4 from homework 7, do the one that's due tomorrow, and put that one and just leave that one on homework 8. So I'll repost homework 7 after class.
all right. Thanks. I just wanted to make sure.
No, thank you for pointing that out. And I'm sorry for I was swapping problems around between homeworks from a previous time I taught the class, and I think I got mixed up.
No problem. Thank you.
Thank you. Okay, so homework 7 I'll repost. There's no harm if the harm is if the worst that's happened is that you did homework problem 4 or too early, and in which case you could just hand it in again next week. And I'm sorry, it would have been hard to do that problem without having discussed that material in class. Apologize for that. Okay. All right. Are there any other questions? Thanks, Tyler, for catching that. Yeah, I thought for homework 7, I was intending to pick out integration problems that we would have had sufficient material by today, at least, to do them. But I'm sorry if I mixed up. Okay. Any other questions before we get started again? So last class, we showed the equivalence of or the equality. So for that, we showed that every Riemann integrable function is Lebesgue integrable, and in particular, the integrals agree with each other. So we recover the Riemann integrable functions via the Lebesgue theory. And also this clarifies something as well. A question about Riemann integrable functions. I just want to make this remark that it was a little bit unclear which functions were Riemann integrable, right? You could say a function is Riemann integrable if and only if you define these upper and lower Riemann sums, and if and only if these two objects have the same limit each other. It's not that necessarily useful of a characterization, right? Because it's hard to compute the upper and lower Riemann sums for a function. But now, at least we have a different characterization of those Riemann integrable functions, namely those measurable functions, which are bounded and have bounded support, right? All such functions are Lebesgue integrable, and hence, right. So then, for example, there are these questions about, how many discontinuities could a Riemann integrable function have, for example. Well, we know from this theorem right now that you can have discontinuities as long as your discontinuities happen on a set of measure 0. You're okay, right? You're Riemann integrable. So because you can compute the Lebesgue integral of such a function, right? So this is you're very welcome to think of an integral of functions as in the Riemann sense, and just know now that you have a kind of a better characterization of which functions are Riemann integrable. When I teach real analysis, I like to just show you how to compute the Riemann integral of continuous functions, because like any further refinements are a little bit silly, because you can only get so far somehow using the Riemann theory, and it's better just to prove this theorem, I think, in a subsequent class. So that I just want to make one more remark about this theorem that we proved last time. Gives us a nice characterization of Riemann integrable functions. Okay. So the next, we're now on stage 3 of building the Lebesgue integral, or building the collection of Lebesgue integrable functions. And the class we'll consider here are non-negative functions. So we're going to drop the assumption, we're going to drop the hypothesis that the support of the function is bounded. So in particular, these functions can be supported on all of the real line. And we're going to drop the requirement that the functions be bounded. So we're going to allow for functions that are unbounded. So we'll consider the class of functions in the extended sense, possibly taking the values plus or minus infinity. And we're not going to throw those out. So we're going to allow such functions in our in this category. We will then tell you whether or not such a function is integrable or not, right? So there will be functions in this category which are not integrable. Whereas in the previous category, everything in the previous category we could define the integral of, right? We could so here we're going to start making distinctions between functions which are Lebesgue integrable and which are not. Okay, so let's get started. So the definition again is going to be pretty intuitive. So we'll take f. F is going to be a function from Rd, taking values in the extended reals. So these closed brackets means I'm allowing for the values plus and minus infinity. And we're going to assume that f of x is positive, not negative for every x. So I guess what I mean rather than write this. So it's I can write f lands in the right half extended real line. Okay. So then the definition is as following. So the Lebesgue integral of such an f is defined to be the integral over Rd of f of x mu dx is defined to be the supremum over all g, which I'll tell you which g's are in a second, g of x mu dx over Rd, where the sup is taken over all g, such that g lies in the class of integral of the previous class of functions, which we understand, such that g is bounded. Well, such that one, g is non-negative and controlled by f. G is bounded, and support of G is finite. So this is why we're building in stages. We learned how to integrate the functions on the right that were on the right. So this definition only makes sense if we know how to compute this object. We just take any G that's bounded as supreme support of G finite, then we know how to compute the integral, and we take the supremum over all such G, and that's the Lebesgue integral of F. That's it. Of course, now this this is if F is bounded and the support of F is finite, then this supremum is realized by just the integral of F. So it agrees with our previous definition. So remark, the soup is either finite or infinite, right? So these are the two options. There's nothing that says that this supremum over here can't be plus infinity. We're going to allow for plus infinity in soups of sets of numbers. And if it's finite, so if this is finite, then we say F is integrable. F is Lebesgue. Integrable. Okay, so on the one hand, this is the definition of the integral up top. This is the integral of F, and then we say F is actually integrable if this number is finite. Okay, so it's simple enough. So some examples. Well, just a couple, maybe a second remark first. If E is an RD, is measurable, F is positive, not negative, then F times chi E is also non-negative, and we can and we define the integral of F over the set E is defined to be the integral of F times chi E over RD. All right, so we just multiply by we want to define an integral over, sorry. If we want to define, sorry, just give me 1 second. If we want to, integrate a function over a set, this is how we multiply by the characteristic function of that set and just integrate that function. So some examples, which we'll get to in a minute. We'll get to at least doing one of these examples of functions that we can now compute the integral of. F of x, say, is defined to be equal to absolute x to the minus alpha if x is less than or equal to 1. And f of x is equal to, say, 0 if absolute x is bigger than 1. This is integrable if alpha is strictly less than d. And f of x, so I might give some of these as homework, but we'll do it in one of these examples in a few minutes. Say is 1 over 1 plus x to the alpha is integrable if alpha is bigger than d. So, for example, this first example up here, d equals 1. This tells you how to compute x to the minus 1/2. Right. This is integrable. Okay. Right, which you would do kind of tongue in cheek in the sense of in the Riemann sense as well, defining by taking by defining an improper integral and then saying that the antiderivative of x to the 1/2, x to the minus 1/2 is x to the 1/2 up to a constant, and then evaluating and taking limits as you approach the endpoints. But now, okay, we'll put this on solid footing in the sense of like these type of functions, which are nice to know how to integrate. Some properties. So let's again restate the set of properties that we have, and I'll add to them a little bit. So the properties. One, we still have linearity. Under this definition, I won't check all these in class. We still have additivity. Where most of these properties are going to follow immediately from the corresponding properties for functions that are bounded with bounded support. 3, we still have monotonicity. 4, if G is integrable, and f is less than G, then f is integrable. So if you can bound the non-negative function above by an integrable function, then the function is integrable as well. 5, f is integrable implies f is finite almost everywhere. Write this more precisely. Implies f of x less than infinity for almost every x. Okay, so this is a new type of property because we just didn't allow such functions before. So 5 is new. And 6, we had this property before. If f is equal to 0, this implies that f is equal to, if integral of f is equal to 0, then f is equal to 0 almost everywhere as well. So every property except for 5 is similar to what we had before. So let's just look at 5. So let's let ek equal to the set of all x such that f of x is bigger than or equal to k, and e infinity equals the set of all x such that f of x is infinite. Okay. Then integral of f is bigger than or equal to this, right? Because we're at most throwing away some points, which is bigger than or equal to k times the measure of ek. In particular, this means by dividing by k all the way through, measure of ek is less than or equal to integral of f times 1 over k goes to 0 as k goes to infinity. So the measure of these sets tend to 0, and we know that ek converge, decrease to e infinity, which implies that measure of e infinity is equal to 0. Okay, so that's the proof of 5. The measure of the set for which f is infinite is measure 0. and this makes intuitive sense, right? If you have positive, if you're infinite on a set of positive measure, then that should tell you that the integral is infinite. Um, okay, so um, the real meat now, or the real reward, is in these convergence theorems. So, sorry, any questions up until now with the definition or with any of these properties? Property one here is a little bit delicate, but you can refer to the book for that. Just as a matter of carefully. So no, there's a soup on the right hand side. Just kind of carefully choosing when to take the soup. The soup. Property one follows. So sorry, any questions up until now? Okay. So like I was saying, the real meat comes in the convergence theorems. So the basic question if f is non-negative, the basic question within this class of non-negative functions, and if you have pointwise convergence almost everywhere, does or when does integrals of the Fn converge to integral of f? Okay. So as with everything in life, this is false in general. Okay. And it's not hard to write down examples where this has to fail. So example, if we take Fn of x to be equal to n if 0 is less than or equal to x is less than 1 over n and equal to 0 otherwise. So the functions look like this, just rectangles. We discussed a version of this example a couple classes ago. Then, let's make this open set here. Sorry. Then Fn of x tends to 0 for every x, right? But integral of Fn is equal to 1 for every n. So integral of Fn does not tend to which is just equal to 0. Okay, so this is a basic counterexample. So one way of trying to refine this is, what do we need to require so that this is true? What do we need to require about the sequence so that we can interchange limit and integral? And one kind of basic tool, one estimate that we have, this is pretty powerful, which is called Fatou's lemma. Well, whereas we might not have convergence, we have the following estimate. So if Fn sequence of measurable functions all non-negative, if the limit as n goes to infinity of fn of x is equal to f of x almost everywhere for almost every x. Then, so if you have pointwise convergence almost everywhere, then the integral of f is less than or equal to the limit of the integrals of the fn's. And this is fine in our previous example, right? Or our previous example that is not a contradiction to Fatou's lemma, right? Because we have one on this right-hand side. This is just equal to this. In fact, has a limit. It's just one, and this is equal to 0. So the Fatou's lemma just says 0 is less than or equal to 1 in the context of this example that we had in the previous board. But the nice thing here is we can put lim inf here. Okay, so how do we prove Fatou's lemma? Well, we're going to try and make it in this context an application of the bounded convergence theorem from last class. So we need to go back to what we mean by integral of f, right? So let g be any function, any measurable function, such that g is bounded above by f, g bounded, and support of g. The measure of the support of g is finite. And so now we want a sequence of such functions, gn of x, to be defined to be the minimum of g of x and fn of x for each x. We just take the minimum of these two functions. Then Gn inherits these properties, the nice properties we want from G. Then Gn is measurable. It's supported on the support of G, right? It's never non-zero outside of the support of G. And we have this type of convergence. Since eventually, and this follows because since eventually, by looking at large enough n, Fn is bigger than or equal to Gn, right? Because the Fn's converge almost, this is almost ever, of course, the Fn's converge to F, G to low F, and so we're just looking at the minimum between G and Fn's. Eventually, if Fn's is to converge to F, it has to get above G. So these Gn's have to converge to G, right? Eventually, Gn for if you fix an x for large enough n, Gn of x is just going to be equal to G of x, right? Okay, but now we can apply bounded convergence theorem to the Gn's. By bounded convergence theorem, integral of the Gn's converges to integral of G. Since the Gn's are all bounded and they have bounded support, supported bounded measure. But by construction, Gn is less than or equal to Fn. And this by monadicity implies that integral of Gn is less than or equal to integral of Fn. Right? So therefore, integral of G is less than or equal to the limit as n goes to infinity of integral of Fn. And then take sup over all of such G. Oops. Now take the soup to obtain integral of f is less than or equal to lim inf as n goes to infinity of integral of fn. Okay. Okay, does this make sense? Does anyone have any questions? Okay. All right. So now let's start. Reaping the consequences of Fatou's lemma. So corollary, the first corollary is that if f is a non-negative function measurable, f in a sequence such that fn of x converges to f of x almost everywhere, and if fn of x is less than or equal to f of x, then in fact we have equality. Okay, and the proof of this is not hard. So fn is less than or equal to f almost everywhere implies that the integral of fn is less than or equal to integral of f for every n, which implies that the lim sup fn is less than or equal to integral of f. And then we also know by Fatou that this is less than or equal to lim inf. Okay, so we just rigged it so we had a bound from above. We bound the lim sup, but from above by the integral of f. So that the hypothesis of this theorem are just so that this first estimate on the left holds, and then Fatou's lemma is the real meat. This is a non-trivial bit. We have this by Fatou's lemma, but now since lim inf is bigger than lim sup, these guys must have a limit, and the limit must be integral of f. Right, so that's that. And a second corollary is called the monotone convergence theorem. If, and this is now immediate from what we just proved, if fn is measurable non-negative and fn's increase to f, then the limit then say fn then limited interval can be interchanged. So if you have an increasing sequence. Okay. So that's the monotone convergence theorem, and see it's an easy consequence of Fatou's lemma. A last corollary, another corollary. So suppose we have a series. So suppose ak of x be non-negative measurable functions, and consider the series such a series. Then the integral of the sum over k's of the ak of x's is equal to the sum over k's of the integrals of the ak's of x's. So you can exchange, in this case, you can exchange integral and sum, and this is going to be a consequence of the monotone convergence theorem. So, in particular, if this integral is finite, then this series converges for almost every x. All right, so this is, we can interchange summation and integral as long as we have non-negative functions in the sum end. And if the series obtained by integrating term by term converges, then the series itself has to converge pointwise almost everywhere.
Can you explain again how you obtained this corollary?
How we obtained this corollary?
Yeah.
Let me argue the proof. Yeah, I haven't. Okay. I haven't.
Okay, thank you.
It's not. It's almost immediate, but it takes a couple lines of argument. Let me do that now. Yeah, sorry, I haven't explained yet. Okay, let me. I'll do the proof. So proof. Just let's let fn of x so equal the partial sum, the nth partial sum. And let's let f of x equal the full series. Okay, then the fn's are measurable. They're increasing, right? Because the AKs are non-negative functions for every n. And the fn's converge to f, right? Just formally converge to f. So since integral of fn is equal to the sum, so just by linearity, okay, for every n. So since each fn is just a finite sum, you can interchange integral and finite sum, right, for every fixed n. Now we can apply monotone convergence, and since implies that the integral of f, this is the integral of the AKs. Okay, and for the last property, since we proved earlier in the class the fifth property of the integral. AK, this is an integral function, implies it must be finite almost everywhere. This was property 5. for any integrable function. The function itself must be finite except in a set of measure 0. Okay, so this is nice, right? We can interchange summation and integral. You're just using monotone convergence theorem. Any questions?
I mean, I find it quite surprising because different literature present the proofs in different orders.
Yeah.
So sometimes they prove the monotone convergence theorem first, then lead to factor lemma, then lead to the corollary, which I think it's also called dominated convergence theorem, isn't it? But then, yeah, things just swap around. So
yeah,
a
so
little bit surprising, a little bit confused.
Yeah, we haven't gotten, so at the last one, the culmination we'll get to is something called dominated convergence theorem. So we haven't quite gotten to that. We can present that in full. That'll be in the context of arbitrary sequences of measurable functions, not necessarily non-negative ones. But yeah, these, like, as you might expect, this is an old theory, and so there are a ton of different, slightly different takes on how to present it. I really like this presentation. It's it builds up quite nicely, quite naturally, and yeah. But you're right. You're right. There's many different takes on integration theory. If some of you may have taken Richard Melrose's class, a functional analysis class, or maybe taking it, or so this is where he also teaches Lebesgue theory, and he does this completely opposite from the way it's done here. So he only he does integration first, and then from integration he builds measure. So there. So not only can you present these convergence theorems in different order, you can also present the entire theory somehow in different order. He gives a very hard to understand definition of what integrable functions are, and then from there you can in fact build a Lebesgue measure from this definition as well. So there are a lot of different takes on this subject. I'm partial to the one that I'm teaching, of course. I've chosen this approach, but yeah, everyone is welcome to read up on different sources and pick their own favorites. It's a matter of often when an old subject like this, it becomes a matter of personal taste, and we all have different tastes. So yeah, good excellent point. Like there's no sent from above order of things or order of operations. So we build this theory. This is just one take on it, and this take is also refined because we're only trying to construct Lebesgue measure and Lebesgue integral as well, as we've seen some other times. So if we want to measure an integral in general, there's probably different order of things is possibly more efficient. Okay, so let me give you a couple of applications. One application. Some applications of this theory we've built so far, or you could think of these as corollaries as well. One that comes up often in probability theory is called the Borel-Cantelli lemma. I don't know if it comes up. Okay, so it used to come up a lot in exercises I did when I took a probability class. So I don't know how much your professional probabilist uses Borel-Cantelli every day. I just assume they use it every day because I remember having to use it in every problem I ever solved in probability theory somehow. So Borel-Cantelli lemma is if you have a sequence of sets, measurable sets, such that their measures are summable, the sum over k of the measures of ek is finite, then, and there's various different versions of the statement of this as well. So then I'm just going to write down an easily obtainable one. Then the measure of the set of x such that x is in ek for infinitely many ek equals 0. So if you can sum the measures of the sets, then x can't, then for any point you take, it can't be, it can only be in infinitely many of these sets on a, the collection of points that can be in infinitely many of these sets has to be a measure 0 set. So if you pick a point at random somehow, then it can only be infinitely many of the EKs. So the proof is just an application of the previous corollary. So let's let AK of x to be equal to chi, the characteristic function of the EKs. And then we can rephrase the conclusion. So then x is in ek for infinitely many k, if and only if this sum is infinite. So, but we're assuming that the sums of the measures of the EKs is finite, which implies that this integral of the AKs is finite, right? That's exactly the previous statement, right? The integrals of the AKs is equal to the measure of the AK, right? So AKs are just the characteristic functions of the EKs. So we're assuming this is finite, but then this is equal to this. This is. Let me just write this is equal to measure of the EKs, which is finite. But then now this implies that this, by the previous theorem, is finite almost everywhere, right? So, so because of this and this, we know that x, if x is in infinitely many EKs, then or that set has measure 0. The set of such x has measure 0. Okay, so that's Perel-Cantelli. And so this is our first application, and our second application is we can actually compute. Let's compute some integrals. Let's compute. So compute some integrals. So let's let our example is going to be 1 over x to the d plus 1 if x is not equal to 0, and equal to 0 if x equals 0. Claim f is integrable outside any ball. So as long as I remove the origin, as long as I move a ball around the origin, f is integrable outside that ball. And I can give an estimate integral over the set x bigger than or equal to epsilon of f of x dx is less than or equal to some constant over epsilon for some finite constant. So this is our this is what I meant by compute integrals. We're going to estimate some integrals. Computing integrals exactly does happen quite a bit in real life. But for now, let's just estimate. Let's learn how to show that these is an integrable function. Oftentimes, an estimate is sufficient when you're dealing with integral. This integral is an ugly integral sign. Okay, the proof is we're going to get back to one of our old Fourier analytic techniques. Is we're going to chop everything up into dyadic regions. So let's let AK equal to the set of all x and RD, such that 2 to the k epsilon is less than x is less than 2 to the k plus 1 epsilon. So we're just going to divide into annuli. Like this. This is with 2 to the k epsilon. And let's let g of x to be the sum from k equals 0 to infinity of ak of x, where ak of x is equal to 1 over 2 to the k epsilon to the d plus 1 times chi ak of x, the indicator function over the ak's. And right, this is going to be our, so we've cooked this up so that this function g is always bigger than or equal to x. So then f of x is less than or equal to g of x, and hence the integral of f is less than or equal to integral of g. And we can compute explicitly now the sum of the AKs. So note AKs, each of these annuli is just given by dilating the previous annuli by 2 to the k. So AK is equal to, by epsilon 2 to the k, right? 2 to the k epsilon times 2 to the k times A, where A is equal to set the unit annulus. So the set of all x between 1 and 2, an absolute value between 1 and 2. And this implies we know the measure of this annulus, right? So that implies that the measure of the AKs is equal to 2 to the k epsilon times d times the measure of A. Which is finite, right? It's like measure is like 1. Some factor of pi, right? It's the volume of the ball of radius 2 minus the volume of the ball of radius 1. So it's right there, some factor involving pi. Okay, so now we can compute integral of g. Integral of g is just equal to the sum from k equals 0 to infinity of the measures of the AKs divided by 2 to the k epsilon to p plus 1, which is equal to the measure of A times the sum, let me give myself some more room, which is equal to the measure of A times the sum of 2 to the k epsilon d divided by 2 to the k epsilon d plus 1. And this sums up to c divided by epsilon, some constant divided by epsilon. You see there's a 1 over epsilon left. And we're done. and in fact, what you could see, you could in fact have rescaled up from the beginning. Um, and just drop the epsilons just by rescaling. Okay. So, so you see the key point in this proof was that this d plus one, so the rate of decay here for this function was d plus one here. But in this proof, you see that all we needed was to beat d, right? So as long as I had a power, as long as I decay polynomial with some power bigger than d, this proof will go through without change, right? Because I'll just get some exponential sum, some geometric sum with the rate with a positive exponent, as long as the power of the denominator is bigger than the power of the numerator. And then you'll get a different factor of different power of epsilon at the end. But in general, this takes care of the example you had in the first slide of the day. If I define f alpha of x to be equal to x minus alpha if x is less than or equal to 1, and 0 if x is bigger than 1. Then it's integrable if alpha is less than d, the dimension, and if I define g alpha of x, this is the example we just covered. Say it's 1 over, to get rid of the problem at the origin, I'll just make this 1 at the origin, x the alpha. This is integrable if alpha is bigger than d, any number bigger than d. So if I have polynomial decay at infinity, where it's faster than the x to the minus dimension, then I'm integrable. If I want to be integrable at the origin, then I need to have growth at the origin that's slower than x to the minus the dimension of the space. So this is a good rule of thumb. And right, this reflects, like, remember, 1 over x dx is just barely in dimension 1, right? 1 over x just barely diverges, right? At both the origin and infinity, right? It's like log of x, diverges like log of x. So that's the borderline polynomial behavior. If you beat 1 over x by a little bit, then you're okay. Okay. So, any questions about this example? I'm pretty sure I gave you examples this week in homework to that are of this nature to work with. So I know this is impossible to follow as I fly through this in class, but you try and work out these examples on your own, and think about why this is a nice way to do the proof. Basically, a lot of things come down to knowing how to sum up a geometric series, right? If you just remember, it's a constant theme throughout your analysis classes. So, the nice thing about Lebesgue integral and about these corollaries that we've deduced from Fatouzlem or this monotone convergence theorem business is that we can is that a nice way to estimate integrals is convert them into sums of this form. And we know that we can, if we have non-negative terms, we can interchange freely summation and integral. So that this becomes now a powerful technique for estimating integrals. So yeah, never forget that. Okay. Yeah, when in doubt, chop into dyadic pieces. This should be the technique that you learn from this class. When in doubt, chop everything up into dyadic pieces and see what happens. Okay. So the general situation. So stage 4, maybe. General situation. The following definition. A function f, a measurable function f on Rd. So now we're now just at any measurable function on Rd, is called integrable if absolute f is integrable. In the sense of the previous definition. Okay, so that's it. So now how do we compute it? So how to compute? How do we compute this? Well, we just try to put ourselves in the context of the previous definition. Sorry. So set f plus, I guess I put these as superscripts, f plus of x to be equal to, this is the positive part of x, it's the maximum of f of x and 0. And let's set f minus of x, this is the negative part of x, to be the maximum of minus f of x and 0. Okay, and then note that f plus and f minus are both non-negative functions. And since the Lebesgue theory is so nice in that it doesn't care how we slice and dice functions up, right? We can slice this up no matter what the sets. So what I mean is that the function might be crazy, right? Right. Remember that like the support of the positive part and the support of the negative part might be crazy sets, but they're measurable. So that's all we need. And f is equal to the sum, right? The difference rather. It's equal to this the positive part minus its negative part. And also note that both f plus and minus are less than or equal to absolute f, okay? Which imply that f plus and f minus are integrable if f is, right? So if f is integrable, then so are f plus and f minus. And we just define integral of f is equal to the integral of f plus minus the integral of f minus. That's it. Okay, so yeah. Okay, so a couple remarks. Any questions about the definition? Okay, so some remarks. Let's try and flesh this out a bit. Remarks. We will identify. So now we're going to start thinking about the class of integrable functions, and we're going to want to think of this as a set or as a space of functions or a set or things of this. So we're going to define equivalence classes of functions. So we identify f equals g if f equals g almost everywhere. Their integrals agree. Integrals agree. Their integrals already agree, and we're just going to identify these functions. If I have f equals f1 minus f2, equals G1 minus G2, where all F1, F2, G1, G2 are all bigger than or equal to 0 and integrable. This implies that G2 plus F1, which implies that F1, these are all non-negative functions now. And now we can argue by linearity, integral of G2 F1, and then rearrange and then this, therefore, that integral of f is independent of decomposition, of the way we decompose it into two functions, into a difference of two functions, one being both of those functions being non-negative. So I defined to you this positive and negative part of f, but of course, like you could think of this, you could do this almost every, you could throw away sets of measure 0 and define different decompositions into positive and negative parts almost everywhere. But the point is that you can't change the integral by doing such operations, right? This is independent of how you decompose. The properties of the integral. Integral is linear, additive, monotonic, and triangle equality holds. So same properties we had before. And then, but a more refined property. Let's see, do we have time to prove today? Maybe. Let me state it. At least the more refined property is that we have absolute continuity of integral. So let me state this as a proposition. So I have absolute continuity in the following sense. So let's say f is integrable on RD. Then for every epsilon bigger than 0, maybe I want to call it part 2 epsilon continuity. Let me rephrase how I state this proposition. F D, then for every epsilon bigger than 0, 1, there exists a set of finite measure B, most often taken to be a ball, such that integral on B complement of f is less than epsilon. So if a function is integrable, then you can find a large enough ball outside of which there's only epsilon left of the integral. And 2, this is absolute continuity. For every epsilon bigger than 0, there exists a delta bigger than 0, such that integral over E of f is less than epsilon for every E such that measure of E is less than delta. So this is the so if I fix an f, then for every epsilon bigger than 0, there I can find a set of measure less than delta for which the integral of f over E is less than epsilon. So this is so if I think of the operation E goes to integral f over E, then there's a notion of continuity for this operation, right? Fixing an f and then performing this examining this mapping. Okay. Right. This is a mapping from the measurable sets of RD to the positive real numbers.
Just to clarify, the second point, it doesn't say anything about the continuity of f, just about the integral of f, right?
Yeah, it's so this is like if we fix an integrable function, then we have this continuity property. But viewing this as this function is I haven't given a name for this function. Let's call this if is this function or something, right? So f is fixed, and then we have continuity in this sense. But this is a nice statement, right? It's no matter what you just give me this size. This is why it's called absolute continuity. You just give me a size delta, and then once you give me any set of measure less than delta, then f can't have much integral on that set. It can have only epsilon on that set. So maybe we do should we do maybe I'll stop here and do the proof. I don't think I could do the entire proof in 5 minutes. And I could do part 1 probably in 5 minutes, but maybe I'll rather just do these together next time. I'll rather state this and prove it next time in class. Maybe we can end with sorry, if anyone has any questions, we can do that instead.
For property 3, can you scroll down?
This one?
Yeah, this is for every epsilon, right?
Yep, for every epsilon. So for every epsilon bigger than 0, there exists a delta such that this is true.
And this is true for every E.
For any E that has measure less than delta.
Okay.
Indeed, yeah, it's a strong statement, right?
Yeah.
And it's like a uniform continuity statement, right? Almost. So we call this absolute continuity of the integral. We call this. Okay. These are going to come out of the monotone convergence theorem. Both of these two properties that we'll do next time. So we're really leaning hard on the convergence theorems that we proved. So these are sort of the cornerstones of Lebesgue theory. The monotone, and so the next thing we'll get to in class. So next time, the dominated convergence theorem. This is sort of the grand the grandest of the convergence theorems. Which will just said if you have a sequence of functions that are bounded above by an integrable function, then you can exchange limit and integral. So that's somehow the most general of the convergence theorems, or the most powerful of them. Okay, and of course in the type of stuff that we've been doing before, that we were talking about convergence properties of Fourier series, such theorems, while pretty, are not too much use when we have to try to exploit things like oscillations. So these will be big hammers that will have they're incredibly useful. But then with the delicate questions that we dealt with in the beginning of class, where we had to do things like integrate by parts and stuff like that, dominate things like dominated convergence theorem are of little use. yeah, so um, otherwise analysis would be uninteresting somehow if Thal-Moneta convergence theorem was the end of the story. But these are sort of the fun. It's we had no such tools really with the Riemann theory. So okay, any yeah, go ahead.
Thank you very much.
Any other questions?
So how is the absolute continuity property of that measure related to absolute continuity in general for any normal function, say?
How are these two? How is this related to? Can you rephrase? Can you rephrase the question or restate
I
it?
mean, we have absolute continuity for functions. So for functions in general, like real value functions. Yeah. So how is that related to the absolute continuity in this setting?
Of the integral. I see.
Yeah.
I guess maybe it's just a continuity statement for this map, for this type of map. So right, if I define this map, which it's a funny map, right? The inputs are sets and the outputs are numbers, but this is a function, right? This is a perfectly bona fide function. Once you fix an f, this is a perfectly fine function. I have a domain and I have a target and I have a function. Then this is just a continuity statement for this function, right? So I guess that's the relation. It's a statement about absolute continuity of this particular function. Of course, we're fixing an f at the outset. We're fixing a function f at the outset. So now once you fix an f, now we're not really, yeah, it's somehow f is just going to play the weight of the weight function in this integral. But yeah, it's just, does that sort of answer your question? It's not really a good answer. I'm just saying, well, it is the same if we view this as a function under consideration. The function I sub f mapping e to integral of f over e.
That makes sense.
Yeah.
Thanks.
Any other questions, comments? I also have office hours in 5 minutes or 5-10 minutes. So you can always pick up the discussion there.
Can you synchronize the file?
Yes. Yep. It should be syncing now. Yep. All right, guys.
Thank you.
Thank you.
Thank you.
Stop share.